So how do you get into medical physics? These days, historically there were a lot of routes in. You could do a master's or a PhD in just about any physical science related discipline, and then find somebody to kind of mentor you and train you on the job until you were able to pass a board exam and get certified to practice. That process is much, much more heavily regulated now. It all just changed in the last few years. This is now the process. You don't have to understand it, but basically, because it's a clinical field, if you want to do the clinical side of medical physics, you have to be board certified in exactly the same way that a physician, a surgeon, a radiologist is board certified, meaning you've passed a board exam and you've been credentialed to practice this field. And now, in order to take the board exam at all, you actually have to do a residency in medical physics. The way a physician, a doctor does, a 4-year residency in radiology after medical school, a medical physicist now needs to do a 2-year residency, either in imaging or in therapy, in order to be eligible to pass these board exams. And now, even to get into one of these residencies, you need either a master's or a PhD in medical physics. I mean, this is the easiest route, is to come through a credentialed medical physics graduate program to then get into one of these residencies. There's a way, if you have a PhD or a master's in a different physical science, you can take the courses, just the coursework you would have done in a medical physics program. You can basically pay to take those. We have a certificate program here. It's called a certificate program. And then apply for a residency program. But right now there's a mismatch between the number of people interested in pursuing medical physics and the number of slots in these residency programs. They've moved just this year to a match system, the way medical residents match, where at the end of medical school, you go interview at a lot of medical residency programs, and you rank the programs you like, and the programs rank the candidates, and then an algorithm kind of tries to maximize the happiness function. And they just moved to that in medical physics, except in medical physics, there were about 3 times as many candidates as there were slots. So only 1/3 of the people in the process actually got into a residency program. But I'd say virtually everybody coming from a reputable PhD program got in. All of our students who were in this process this year all got their number 1 choices. So they were all, they all must have been at the top of everybody's list. And so, I think the number of residency programs is going to expand. The downstream demand for medical physicists looks high. It looks like there will be, a need for medical physicists as the, amount of radiation therapy increases. But, in the short term, if you really want to pursue this as a career, I think the PhD is a safer route. And, I suspect most people, coming from a U of C background would be interested in sort of the research aspect of doing a PhD and the problem solving. Not to mention you actually get sort of paid while you're doing a PhD, whereas the master's programs, typically you would be paying. And so, so I'd say, right now, the PhD programs are, a good route to go. So what kinds of places have PhD programs? Not every place does. We have one. We have arguably the oldest in the country. We argue with Wisconsin. We were either founded the same year or a year before them. Wisconsin's very good. They have a large master's program as well as a PhD program. We only take students intending to get the PhD. UCLA, Duke is new about 10 years ago, but they're a strong program. There's some in Canada, of course, and there's a full list. CAMPEP is the organization that accredits medical physics programs, so they have a full list of all the accredited programs right now. So how can you learn more about medical physics here? Well, as was mentioned, we teach a class here. It starts tomorrow. It's called BioSci 29-326, Introduction to Medical Physics. And I teach slightly more than half of it, and one of my colleagues from radiation therapy does part, and another colleague from radiology does a few lectures. And it can actually count as a core bio topics class for you, as a core bio elective. And even though it's kind of feels like a physics class hiding over there, I mean, we have problem sets and we use kind of an engineering textbook. So technically it has quantum as a concurrent prerequisite, but nothing really, we're not starting from Schrodinger's equation at any point. I mean, you kind of need to be vaguely familiar with the stuff that was covered in modern physics, not be completely scared or unfamiliar with Fourier transforms, and be willing to accept that spin is quantized in a magnetic field when we do MRI. But otherwise, I've even had first years take the class and do just fine. So consider checking it out. Medical physics. There's a journal called Medical Physics published by the Professional Society, so that gives you kind of a sense of what research is done. You can come talk to the faculty in medical physics. I'm sort of the liaison for all undergraduate activities. We've had many folks do research with our faculty over the years. Summer research or during the quarter, or BA theses. You're allowed to do your BA thesis under the supervision of somebody in medical physics. And again, I'm a good point person to contact to try to find out about those opportunities. So let me just tell you, are there any questions about the field as a profession? Then I'll tell you about a couple of the projects my colleagues work on. No burning questions? Okay. So we cover basically the whole imaging chain from image acquisition, finding better ways to acquire better images in the first place. So a couple of my colleagues work on PET, which is positron emission tomography, and that's kind of the most science fiction-y of all our imaging modalities. So this is where you inject the patient with a radiopharmaceutical. So basically, a mildly radioactive substance that will hopefully, in the best case scenario, would target something of interest in the body, like cancer cells. That's the holy grail. If you could make a tracer that will only, stick to cancer cells, then you could really sort of see where the cancer cells are in the body. Right now, by far, the vast majority of PET studies are done with fluorodeoxyglucose, which is basically sugar, radioactive sugar, and it shows you, areas of high metabolism, and cancer tumors tend to be highly metabolic, so it's useful. There are some other more specific tracers, and obviously vast amounts of research in trying to achieve that holy grail. But the basic way PET works is you inject this radio tracer, and these radio tracers in PET have to be positron emitters. It has to be an isotope that emits a positron as part of its decay, and that positron will very quickly find an electron with which to annihilate. And when they annihilate, they vanish, and you get a pair of 511 keV photons, right? By mass energy conservation, they have to have the energy has to equal the rest mass of the two particles. And if in general the positron has kind of run out of momentum by the time it annihilates, and so when that happens, the two photons are going to be precisely collinear. They're going to be going precisely in opposite directions. And then you surround the patient with a ring of detectors that are all wired in coincidence, so that when one of these detectors detects a count, the other side of the ring is put on alert and said, okay, if anybody gets a hit within the next coincidence window, we're going to assume that these two came from the same decay event. It would be unlikely, it's not impossible, but unlikely that those came from, it came from a different event. And so at this point, the coincidence just tells you that somewhere along this line, a decay took place. And the old systems would just kind of increment that counter, say, okay, I've now had one count along the line connecting these two detectors, and would then gather millions of counts and put them all into bins, and you would learn something about the total amount of radioactivity along a bunch of different lines through the body. And it turns out that's a mathematical, there's a mathematical problem that can be solved. You can reconstruct functions from the set of their line integrals along lines. That transformation is called the radon transform, and it's solvable. So you could solve for where the activity was in 3D that was consistent with the set of line integrals you measured. Nowadays we can do a little better than that, and actually my colleagues are working with people in physics to do even better than what's currently clinically possible. If you could measure the arrival time difference of these two photons with great accuracy, you would know not that somewhere along this line an event took place, you would know exactly where it took place. If you could do it with about 10 picosecond accuracy, you could put the event back to where it, to about the resolution level you're hoping to get. Right now the current fastest detector electronic combinations on the commercial scanners are about 300 picoseconds, which gives you 10 centimeters. Remember, we're talking about the speed of light here. It gives you about 10 centimeters of localization. And so you can fold that information into your attempt to put the radioactivity back where it belongs. It improves the images, but if you could really push to that 5 millimeter resolution, that would be spectacular. And so Henry Fritsch is working on a picosecond timing project. Obviously the particle physics world is interested in these things. At some level they already have them. The question is, can you make it robust enough and cheap enough to put into a medical product, where the whole product is going to cost $1 million, not $1 billion like a detector at CERN. So that's been a very interesting collaboration. Oh yeah, there's just another view of PET. So these are this is what a PET image looks like. This is a CT image, X-ray computed tomography image. Nowadays, every PET scanner you buy is a PET CT scanner. It has both on one gantry. It's kind of like a washer-dryer 2-for-1. And the reason for that is twofold. One, as we move towards this holy grail of getting tracers that really only target tumors or really only target what you're hoping for, at some point your PET image would be just a dot in space, and you're like, okay, that's nice, but where is that in the patient? Here with this radioactive sugar, we can see this is the left ventricle of the heart, this is the bladder. You can kind of see the outline of the body, but having the CT gives you, the anatomical image on which to overlay this metabolic activity. The other thing the CT gives you is it allows you to form a better PET image by correcting for the attenuation of these 511 keV photons as they leave the body, right? To the extent that some of them get reabsorbed, the quantitation, even the qualitative appearance of the PET image would be inaccurate. And so this provides you an attenuation map, not exactly at the same energy, but just gives you a lot of information about, well, where are the lungs, right? There's not much attenuation in the lungs. That should be in our model. So yeah, this is just another typical PET image. This is not a good sign, that this hot spot in the lung is a sign of a metabolically active, that's almost certainly a malignant lung tumor, as opposed to a benign, if you'd seen something on a CT scan, you don't know, it might just be a benign, scar tissue left over from something, that is, metabolically active. That's not a good sign. MRI, we've got folks working on MRI. So MRI is based on the principle of nuclear magnetic resonance, where you're manipulating the nuclear spin most of the time of hydrogen. Hydrogen is the strongest, the most prevalent atom in the body, and hydrogen has a non-zero nuclear spin, and you can manipulate it. It has two states, a spin up and spin down. And by manipulating the spin of the nuclei and watching them sort of relax back to equilibrium state, you can make a number of really stunning images. Different tissues, the hydrogen atoms in different chemical environments will relax back at different rates. And so you can do, there's a tremendous number of degrees of freedom in terms of the way you run the MR scanner. And so that makes for very rich research opportunities. And we've got a strong group, Greg Karchmar's group, that runs from, we have a 9.4 Tesla small animal imaging MR scanner, where they can prototype and try ideas, test pulse sequences, and things that work well they can translate, fairly rapidly onto the clinical scanners, which is nice. CT, I personally work on CT, X-ray CT, which is really an extraordinary modality. I mean, it's changed a vast amount in the 20 years that since I started as a graduate student. When I started as a graduate student, CT was still pretty much a slice by slice modality. I mean, it was extremely powerful to get a three-dimensional transverse slice through the body as opposed to just looking at a planar radiograph. But at that time, people were still even printing out the 10 slices you got of the patient on a CT scanner. They'd print them on film and hang them on film boxes to look at like they were radiographs. And the scanners basically are now able to operate continuously, use acquire hundreds of slices simultaneously, and you're basically able to scan from the patient's eyes to thighs, we call it, scan the whole thorax and abdomen while the patient holds their breath. You can acquire this image in about 20 seconds. This is just showing one of the leaps from the 16 slice scanner to the 64. We now have a 256 slice scanner here. This is already 10 years ago. But you can see, here, this is the heart, and these are sort of, this is, the different chunks of data that were being acquired, at different phases of the heart beating. And up here, the heart was more or less, acquired in one single snapshot. And that's one of the hot areas of research in CT right now is cardiac imaging. That's the most challenging organ to image medically because it's moving so rapidly, and there are some pretty fine structures that you would like to be able to detect. In particular, what you're often interested in are the coronary arteries. So these are the arteries that feed the heart itself, right? The heart is a muscle. It needs oxygenated blood to survive, and even though the chambers of the heart, at least two of them, are filled with oxygenated blood at varying times, that's not where the heart gets its own blood supply. It gets its blood supply from these coronary arteries that come off the aorta. As the aorta leaves the left ventricle, it feeds the heart. If you get a severe narrowing in one of these arteries, or a complete blockage, that's basically the cause of most heart attacks. That's called a myocardial infarction. The heart is no longer, some portion of the heart muscle is no longer receiving oxygenated blood, and if that isn't corrected very rapidly, it will, that muscle will die and can't be revived. And so, what you're looking for in the standard way of imaging the coronary arteries is through an interventional radiology. Basically, you thread a catheter from somebody's thigh up through their blood vessels, squirting iodine as you go under kind of video X-ray guidance, so you can see where you're going and not puncture the arteries with your catheter. And so it's an uncomfortable procedure. I mean, the patient's is sedated. It's very expensive because you've got a extremely well-paid interventional cardiologist or radiologist doing the procedure. It takes a certain amount of time. There's recovery time, and so what people are able to do now with CT scanners are so fast that you can basically get these images just with an intravenous injection of iodine. So you inject iodine into a vein, wait for it to, reach the heart, the right side of the heart, get pumped back out, come back in, get pumped into the coronary arteries, and then you try to grab this snapshot of the coronary arteries, which you're then trying to read and look for those narrowings. So even here now, they're exploring in the ER if somebody presents with chest pain, let's do a CT angiogram first. If it's clean, if we see no problems in the coronary arteries, then it's something else. If we see kind of a mild narrowing, there's probably some medication that could treat it. If you see a really super severe artery, then you'll send them to the cath lab, because in addition to sort of visualizing the coronary arteries, you can try to introduce, you can try to open the narrowings using balloons or using stents, kind of put a structure in there to try to hold it open. You can do that in the interventional lab. And I've got a research project where we're looking beyond this. Can you use CT, a video sequence of low-dose CT images to actually watch the iodine perfuse the heart muscle itself? Because one question, if you see kind of a half blockage in one of these vessels, you always want to know, well, is the heart muscle still getting oxygen or is it not? How much blood is getting there? And so, again, you can see this, the iodine is strongly absorbing of X-ray, so you can see the heart muscle will kind of, darken in the CT image, and you can try to, extract some information about just how much blood is getting there from those images. But it's, it's very, very challenging to do it at reasonable X-ray doses. Another big area of research in my department, something some of my colleagues are world famous for, is for image analysis for cancer screening, basically for having taught computers how to read medical images automatically as sort of spell checkers for radiologists. And this began with the canonical screening modality, which is mammography. So, in mammography, mammography is a screening modality, which means it's imaging that's done in asymptomatic patients. So you have no reason to believe that the patient has anything wrong with them, but you're just looking through because some very small fraction of the women you're screening will have, a breast cancer that you would like to detect early. And so, maybe 1 in 1,000 mammograms actually has a true cancer in it. And so it's hard and somewhat tedious work for the, radiologists to read all these screening mammograms, knowing that very few of them are actually going to have an actual cancer. I mean, you'll see there are other things that can look like cancer and that you'll, call a patient back and acquire extra views or do an ultrasound to rule out a cyst, things like that. But, there were, many cases historically where radiologists simply failed to see something that was in one of these images because you're just looking at the same kind of thing over and over and over again. And so the group here developed algorithms that could automatically, extract, regions. This is sort of a suspicious, this little bright patch here is suspicious, and so they could sort of automatically extract such patches and analyze, summarize them by a certain set of geometric and other parameters, and then having built up a big database of cases that were known to be normal and abnormal, they could basically train the computer to classify these patterns as either, potentially, worrisome or not. And then they would flag, this is the actual output of the system. It would put a little arrow, for the, indicating that the radiologist should have a closer look at this area. And so this is something called, the field is called computer-aided diagnosis, and it's been commercialized now. In fact, it's one of the most successful licensing deals the University Tech Transfer Office ever had, because they wrote the patents in a pretty broad way when this first emerged, and so they kind of the company that licensed it kind of cornered the market for a little while, and so this and this kind of work is still ongoing, of course, both on the mammography side, but also in other imaging modalities. So I think there's an example. So for CT scans of the lung. There's increasing amounts of interest in doing lung cancer screening in smokers, basically. So not still asymptomatic, but a group with a elevated risk profile. And again, these are hard to read. You're looking for lung nodules, but you've got all these sort of this tangle of blood vessels and bronchial structures that can easily confuse the radiologist and the computer. But this was another product that was developed. This is something else. So then the last thing I just wanted to tell you a little bit in the last few minutes about a somewhat different project that I'm working on, which is related to X-ray fluorescence imaging. And this involves some work I did at Argonne for a while, and then we're trying to bring it into the Benchtop. And so X-ray fluorescence is a way of, traditionally it's a synchrotron-based modality for trying to image the distribution of metals in a sample. So in my case, I'm interested in biological specimens, and you want to know where the non-radioactive metals are, like iron and zinc and copper, have sort of important biological functions, and then there are metals like lead and mercury that are toxic metals that you would like to avoid. And the way it's done traditionally at the synchrotron is you bring in a pencil beam of X-rays. So maybe X-rays focus down to a 2 micron spot, and they're traveling along this pencil beam, and they pass through your sample. And these X-rays are going to you choose the X-ray energy so that it sits above the K edge, the inner shell absorption binding energy of the elements that you're most interested in. So if you're really interested in zinc, you'll sit right above the K edge of zinc. Because of that choice, you're going to tend to have a lot of photoelectric interactions with zinc. These X-rays are going to knock those K-shell electrons out of the zinc, and the zinc is going to respond often by dropping an outer shell electron to fill the vacancy and emitting a characteristic X-ray. And so then you're trying to gather as many of these characteristic X-rays as you can with this, the biggest, most energy resolving detector you can. Okay? It doesn't have to have any position information. It just needs energy resolution. So you measure, and basically what the measurement, because you can pick out the zinc peak in the spectrum that you collect, the measurement tells you something about the total amount of zinc along the line you illuminated. Okay, this may remind you of what I was talking about with PET. Right, if you know the total amount of a distribution along, well, if you know it along one line, that's all you know. But if you know it along, a bunch of lines through the object, and then you can rotate the object and, measure it along all these lines, you can, you measure a set of data that basically looks like this. This is, how far along the object the line was, and then the rotation angle. And this, in our world, this is called a sinogram. That's just its technical term. But again, from this data, we can use mathematical algorithms. We can invert this radon transform to get images like this that tells us where the arsenic is in this plant root. So this is a plant root that was being studied as a potential way of cleaning up toxic waste. If this plant strongly accumulates arsenic, well, then we can use it to suck arsenic out of the groundwater. And so, the problem with this approach is that it's very tedious. We're measuring one of these lines at a time. And so the approach that I've been taking with my collaborator at Urbana-Champaign is intuitive, but it sort of required, some new detector technology that has become available recently, which is to try to use a pixelated detector, so not a great big monolithic detector, a pixelated detector to really just capture an image of one slice of the object at once. And this relies on the fact that we can control the illumination. We can turn on this process in a way that we can't in PET. In PET, your radioisotope is just emitting everywhere. Here, we can cause this emission by bringing in, say, a sheet of X-rays. So we know that all our characteristic X-rays are going to be coming from the plane that we hit with this sheet. And then we have a pixelated detector trying to make an image of that plane. And basically, in between, we need an optic of some kind, right? We've now got a camera with a sensor. We've got a plane out in space. We need to make one-to-one mappings. Well, unfortunately, it's hard to make lenses for X-rays. So we have to use a pinhole, go back to the old days of optics and make a pinhole camera. But it works, it gives you, one-to-one mapping or one to, a little circle of confusion. The sensitivity is not great because you're not letting most of the X-rays through the hole. But potentially you can multiplex, you could use an array of cameras, an array of pinholes. And so we showed that this worked. We did it out we did it at Argonne, and we made an array of 15 pinholes. This is showing 8, so that we could fill, basically the projection of our object onto our detector wasn't going to fill the detector, so we put as many pinholes as we could to fill the detector. And so this is what it's like to work at Argonne. You're basically working in your experiment goes on in what looks like a boxcar, because it's all got to be shielded with lead, and then you obviously leave the boxcar and close the door when you're going to run things. And so this is the kind of spectrum we could pull off the camera, which was, this was one of the sort of the tricks we were using. The camera is not natively an energy resolving camera. We were just reading it out at a fast enough frame rate such that there was unlikely to be more than one event in any pixel. And so then the magnitude of the signal in that pixel could be related linearly to the energy of the X-ray that interacted. So this is what the raw data looks like. So this is for different slices, so moving the object through that beam. This is for different energy channels. So the iron didn't show up very well. I mean, it's here faintly. The zinc and the bromine, and then we saw 15, 15 slightly shifted views of everything because we had 15 pinholes. And so for any one of these, we could, average these 15 views appropriately together and get, one slice of the zinc and one slice of the bromine, and then we could restack these slices. This is showing that process, and then slot them back in where they belong. And so what this gave us then was a 3-dimensional reconstruction, and this is what our object looked like. We just twisted 3 tubes of different metals together. We could color code it based on, we could label the, the metals that were present. So this was cool. Oh, I forget if this movie, oh yeah, it will work. So I think this was actually the first isotropic 3D X-ray fluorescence image ever made, as far as I know. Other people have now done it in different ways, but it was fun that it worked. And then now we're actually looking at an even different geometry, which partly addresses the problem of the pinhole not letting very many of the X-rays through. And the idea here is we go back to a pencil beam, but we're not trying to measure a line integral this time. We still have a pixelated detector, and we still have a collimator, a physical optic. But instead of just having a hole through the collimator, we have a slit. And if you think about the geometry, the combination of the line and the slit means that sort of any point, any given point along this line, those X-rays can only make it through the slit. There's only really one way to make it through the slit, and they'll end up in, a given column of the detector. And then the stuff over here can go through the slit this way and end up in this column. And so what this allows us to do then is we can basically take the image we get, we can, average collapse in the 3rd dimension. We're just getting extra statistics in letting all these X-rays through. And then reverse what we get and plot things back into the image. So we can fill in our image, one line at a time, but we're, it can still happen faster because we're letting many more of these characteristic X-rays out. And again, we could, if we wanted to be fancy, we could do multiple slits and multiple detectors. And so we did this with we had a zebrafish from one of my collaborators that he had stained with osmium for a different kind of set of experiments I was involved in. And so we used this as a test object, and these are before correcting for self-absorption, and this is after correction. So these are the eyes of the fish, and then that's a side view. So it worked quite well, and actually quantitatively the numbers agreed really very closely with a kind of a gold standard measurement we'd made in a different context. So that was cool. I think we even have, the movie of the zebrafish. So you can see the eyes, the lens of the eye takes up this osmium stain very strongly. So that was cool. You don't need to see that. And so so now what we're trying to do, we just got funding from NIH to build a benchtop version of this system. So to try to do it without the synchrotron, to do it in the lab, And so that presents two major challenges, and this is the last thing I'll say. One, just the flux coming out of any X-ray source is not going to match what we can get at a synchrotron. So it's inevitably going to be somewhat slower, but you only get a limited amount of access to a synchrotron where we can have graduate students work all night with this, and so this will it just gives us more flexibility to play with the thing. And the other challenge is at the synchrotron you have so many photons that you can throw them everything away except the ones at a particular energy of interest. You can monochromatize without losing too much flux. And here we may need to work with polychromatic, with or at least we can monochromatize with the source we chose, but we can't tune the energy. We're going to have to be at 17.5 keV, which is not optimal for looking at iron or something whose K edge is in the 6 to 7 range. But anyway, it's an interesting project. I work more on the data processing, the image reconstruction. The step of how do we correct for all the non-idealities to get from data that looks like this to a fish that looks like a fish. And yeah, that's the main. I'll stop there. I mean, we're interested in using this technique to map the distribution of copper there are some diseases in which dysregulation of copper appears to be strongly correlated with the disease. Whether it's causative or correlative is still an open question, and we think this could shed some light on that. So thanks for your attention, and I'll stop there.